हेलो फ्रेंड्स, आज हम लोग चैप्टर 9 इंस्ट्रूमेंटेशन, कलोरीमेट्री एंड स्पेक्ट्रोफोटोमेट्री पढ़ेंगे। चलिए शुरू करते हैं। यूज ऑफ सेंट्रीफ्यूज मशीन। सेंट्रीफ्यूज मशीन का यूज कैसे करते हैं वो समझेंगे। द स्टूडेंट्स आर ऑफन रिक्वायर्ड टू यूज सेंट्रीफ्यूज मशीन टू स्पिन डाउन सस्पेंडेड पार्टिकल्स of any fluid. There are various types of centrifuges such as laboratory centrifuge, cold centrifuge, high speed centrifuge, ultra centrifuge, etc., which are used for different purposes. The centrifuge machines are delicate instruments and are to be used with care to avoid serious mischief both to the operator and to the machine. Most of the instruments can be run at 3000 to 5000 revolutions per minute. The speed regulator shows steps of increment of speed. The sample of solution should be centrifuged at a desired speed. Very high speed may spoil your material and also will bring about quicker wear and tear of the instrument. For example, if you want to spin down RBC to separate plasma, a speed of 1000 rpm for 5 minutes is enough. Final particle need a higher speed and longer centrifugation time. Lab centrifuge. This is high speed centrifuge. The most important precaution is to counterbalance the hands of the machine. Pour your material in a suitable size centrifuge tube and for counterbalancing take another matching centrifuge tube and pour in it the same liquid or water up to the same level. It is advised to equalize the weight of the two tubes using a Behringer balance by adding or taking out little quantity of the liquid to or from either of the tubes. Then put these tubes on opposite arms of the centrifuge machine. If you have more materials, the other arms of the machines can be similarly loaded. Put the regulator in the zero position and switch on the machine. Gradually increase the speed up to the desired level, allowing the machine to gain a speed after each increment. After the machine has run for the required time, usually for your purposes 5 to 10 minutes in is enough. Switch off the machine or bring back the regulator to zero position and wait until the centrifuge hands come to rest. Will in a speed if the machine is unstable or shakes too much, it indicates that the tubes are unbalanced. Stop the machine immediately and check if by chance centrifuge tube is broken inside the machine or liquid is spilled over. Clean the machine and pick out all broken and loose particles. Photoelectric colorimeter. Photoelectric colorimeter. Photoelectric colorimeter is an instrument which measures intensity of color of a solution by registering the amount of light absorbed by the given solution. Thus, the instrument is better called absorptiometer. ये क्या करता है? मेजर करता है इंटेंसिटी ऑफ कलर ऑफ ए सॉल्यूशन. Colorimeter. There are several types of absorptiometer available. They have the following essential parts. पहला a source of light. दूसरा a device to select a narrow wave band of light from the source. This monochromatic light is allowed to pass through the test solution. In most instruments, this is done by placing selected filter in the pathway of light. In others, such as a spectrophotometer, diffraction, grating, or a prism is used for the same purpose. तीसरा, यह photosensitive element. In most instruments, barrier layer cells are used. The cells are provided with a layer of selenium. When light falls on selenium, it is activated and emits electrons in proportion to the light falling on it. If a galvanometer is connected to measure the amount of electron flow, it will indicate the amount of light falling on the cells. Other instruments use photoemissive tubes in the place of photocells. For cuvette or test tube to hold the test solutions. These are made of neutral gas and glass. It is absolutely essential that all cuvettes used in a particular instrument should possess the same absorptive capacity and hence should be interchangeable. Cuvette or test tube to hold the test solution. These are made of neutral glass. It is absolutely essential that all cuvettes used in a particular instrument should possess the same absorptive capacity and hence should be interchangeable. Fifth क्या है? ये sensitive galvanometer to measure the output of the photosensitive element. Light source, light absorb, adjusting slit, filter, cuvette, photocell, galvanometer. When monochromatic light passes through a colored solution, a certain percentage of the light is absorbed. The two fundamental laws which express quantitatively the extent of these absorptions are those of Lambert and Beer. According to these laws, the optical density or extinction of a colored solution is proportional to the concentration of the colored substance. The optical density OD is defined as the logarithm of the ratio of the incident to transmitted light. The optical density is defined as the logarithm of the ratio of incident to transmitted light, the light emerging out of the solution. Thus, OD is equal to log of incident light upon transmitted light is equal to log 100 upon T, where incident light is taken as 100% and T is the percentage of light transmitted. is equal to log 100 minus log t is equal to 2 minus log t. Thus, when the transmittance of solution is 50%, the OD will be 2 minus log 50 or 2 minus 1.699 is equal to 0.3. Since the OD is directly proportional to the concentration, it follows that concentration of unknown upon concentration of known are standard. OD of unknown upon OD of standard, or concentration of unknown is equal to OD of unknown upon OD of standard into concentration of standard. Instruments vary in their mode of calibration of the galvanometer. Most instruments show calibration both in optical density, extinctions, and percentage transmission scale. If the readings are taken in percent transmission, then for calculation purpose, it has to be converted into optical density according to the formula. Instruments vary in their mode of calibration to the galvanometer. Most instruments show calibrations both in optical density, extinctions, and percentage transmission scale. If the readings are taken in percent transmission, then for calculation purpose, it has to be converted into optical density according to the formula OD is equal to 2 minus log T. Use of blanks. In colorimeter analysis, preparation of blank becomes necessary because some color comes from the reagent, etc., which is in addition to the color produced by the substance being estimated. Hence, if blank is prepared using all reagents except the substance which is being measured and its optical density value subtracted from the OD of unknown and a standard, the remaining values represents the true optical densities. Hence, if the blank is prepared using all reagent except the substance which is being measured and its optical density value subtracted from the OD of unknown and standard, the remaining values represents the true optical densities. Choice of filters. If the concentration and optical density relationship is to be linear, monochromatic light is necessary. In nearly every case, the correct wavelength to select is that of the light which is most strongly absorbed by the colored solution. This is generally a color which is complementary to the color of the solution, that is, for blue solution to red filter, red solution to green filter, and for yellow or brown solution is a blue filter. Okay, blue solution, red filter. For red solution, green filter. And for yellow or brown solution, blue filter. Operation of the instrument. Use the instruction manual of the instrument or take the help of a technician. Broadly, the steps are as follows. Insert the correct filter at the right place. Take distilled water in one cubit, put it at the place provided for it in the machine and switch on the instrument. Leave it to warm up to and switch on the instrument. Leave it to warm up to for about 4 to 5 minutes. Switch on the galvanometer if not already done. Adjust the needle of galvanometer and bring it to position 100% transmission of zero optical density. Now filter or fill another cubit with a blank test and a standard solution in succession and put them in place of water and read their optical densities. After completion of your reading, switch off the instrument and disconnect it from the mains. Thoroughly clean the cubit first with dipole and running water and then rinse with distilled water both inside and outside of the cubit. Do not touch the optical part of the cubit with fingers lest you have finger marks on it. Absolutely clean and transparent cubit are essential. Calculation: concentration of substance in the unknown is equal to OD of unknown minus OD of blank upon OD of a standard minus OD of blank into concentration of the substance per 100 ml of the standard solution. For simplicity and quicker work, but not without loss of some accuracy, a calibration curve depicting the OD at various concentration of the substance can be drawn to calculate the result in day-to-day use, but it is always advisable to include a standard with each of the tests. A spectrophotometer. A spectrophotometer has all the basic components of a photoelectric calorimeter with more sophistications and accuracy. The main difference is the way by which it selects a narrow wavelength using a prism or diffraction grating in place of color filters. Also, since the light source in a spectrophotometer is a tungsten, quartz and or deuterium lamp, we can take measurement in visible, ultraviolet and infrared regions of the spectrum. The use of UV region of the spectrum gives us the ability of measuring even those analytes that do not produce a color solution by using their nature of absorbing light at UV infrared wavelength. Hence, the spectrophotometer is not only sensitive and more accurate, but it also increased the number of different analytes that we can estimate. Selection of the region or maximum absorption of a colored solution. Principle: when a pencil of rays of different wavelengths of light is allowed to pass through a colored solution, some rays are more absorbed than others. Maximal absorption is seen with rays of complementary color to that of the solution. For maximum sensitivity of the color measurement, it is imperative to select a light which will be maximally absorbed by the colored solution. Reagent: cobalt acetate solution. Prepare 3% solution in 1% volume by volume HCl. Procedure: measure the optical density of the cobalt acetate solution in a photoelectric colorimeter using different filters and using water as blank. Plot the OD against wavelengths of the filter used and find out the suitable filter for measurement of the color of the cobalt acetate. प्रोसीजर क्या है एक बार फिर देखते हैं. तो measure the optical density of the cobalt acetate solution in a photoelectric colorimeter using different filter and using water as blank. Plot the OD against wavelength of the filter used and find out the suitable filter for measurement of the color of cobalt acetate. Verification of Lambert's-Bayer's law principle. According to this law, the OD of the solution will be proportional to the product of the concentration of the color substance and the depth of the liquid through which light passes. If the depth of the liquid is kept constant by using same or similar concentration or similar container of liquid equal width, then OD is proportional to the concentration of the solute in solution. This relationship holds good only with certain concentrations beyond which the proportionality fails. Reagent: cobalt acetate solution. Purpose: 3% solution in 1% volume by volume HCl. Second, 1% volume by volume HCl. Procedure: pipette 0.5, 1, 2, 3, 4, 5 and 6 ml of cobalt acetate solution in different test tube marked from 1 to 7. Make up the volume in each test tube to 6 ml by adding a requisite amount of 1% HCl. Mix well and measure the OD using the blue filter. Plot your OD reading against concentration of cobalt acetate and find out the range of concentration within which OD is proportional to concentration. The result will give an idea of the range of concentration of cobalt acetate within which measurement should be made. Plot your OD reading against concentration of cobalt acetate and find out the range of concentration within which OD is proportional to concentration. The result will give an idea of the range of concentration of cobalt acetate within which measurements should be made. अब आते हैं स्पेक्ट्रोस्कोप से. Many biological substances possess characteristics light absorbing property. When a white light is allowed to pass through a solution containing a substance which absorbs light of a particular wavelength and the emerging rays are viewed through a spectroscope, one will observe one or more dark bands in the solar spectrum. These dark bands will correspond to those rays of light which have been absorbed by the solution. Thus, by accurately noting the position of the absorption band in the spectrum, it is possible to identify the substance. Various blood pigments and porphyrins are identified in biological fluid within the with the help of a spectroscope. Okay, spectroscope. Many biological substances possess characteristic light absorbing properties. When a white light is allowed to pass through a solution containing a substance which absorbs light of a particular wavelength and the emerging rays are viewed through a spectroscope, one will observe one or more dark bands in the solar spectrum. These dark bands will correspond to those rays of light which has been absorbed by the solution. Thus, by accurately noting the position of the absorption bands in the spectrum, it is possible to identify the substance. Various blood pigments and porphyrins are identified in biological fluid with the help of a spectroscope. Spectroscopes are available in various types for ordinary work. In work for ordinary work, a direct vision spectroscope is very useful. It consists of a prism situated behind an adjustable slit and an adjustable eyepiece. When a pencil of sunlight is passed through the prism, it disperses into solar spectrum, which can be which can be seen through the one eye piece. Okay, thus by accurately noting the position of the absorption band in the spectrum, it is possible to identify the substance. Various blood pigments and porphyrins are identified in biological fluids with the help of a spectroscope. Spectroscopes are available in various types for ordinary work. A direct vision microscope is very useful. For ordinary work, a direct vision spectroscope is very useful. It consists of a prism situated behind an adjustable slits and an adjustable eyepiece. When a pencil of sunlight is allowed to pass through a prism, it disperses into solar spectrum, which can be seen through the eyepiece. Some of the spectroscopes have built-in a scale to indicate the wavelengths of dispersed ray in angstrom unit. 10 angstrom is equal to nanometer. With the help of the scale, the position of the various absorption bands can be characterized. Some of the spectroscopes have built-in a scale to indicate the wavelengths of dispersed ray in angstrom unit. 10 to the power 10 angstrom is equal to nanometer. With the help of the scale, the position of various absorption bands can be characterized. In the solar spectrum, several black lines are seen. These are called Fraunhofer's lines the, and are thought to be caused by absorption of certain rays of light from sun rays by the atmosphere. Among them, B, C, D, E, B, and F are clearly seen. Table 5 and are of great help in ascertaining the position of absorption bands, especially when a scale is not provided with the instrument. A scale adjustment screw, fastening screw, housing for a scale, slit. Slit adjustment ring, eyepiece, spectroscope, position of Fraunhofer's lines, B red, wavelength 687.7, C red, wavelength 656.3, D orange yellow 589, E green 527, small b green 518, F blue 486, G violet 430.8. Operation of the instrument. The instrument is first held in hand and is viewed through its eyepiece in good daylight. The slit is gradually closed with the help of its adjuster until the spectrum is neither very bright nor very dark. The eyepiece is seen. Then the eyepiece is the eyepiece is then moved forward and backward until Fraunhofer's lines are well seen. If the instrument has got a scale, it is adjusted with the help of the scale adjustment screw so that the graduation mark 589, usually shown as biggest line, coincides with D lines present in the orange-yellow region of the spectrum. The scale adjustment screw is then unscrewed by tightening the fastening screw so that the scale is not displaced accidentally. Now the instrument is ready and is clamped to a stand on in horizontal position. The solution to be examined is put in a good glass test tube 1 cm. diameter and is held vertically in front of the instrument with the help of another clamp. If the spectrum appears dark, it may be necessary to open the slit slightly. It may be noticed that at one or more positions in the spectrum there is no color and which appears as dark bands. The location of each dark band center of band is read on the scale. If there is no scale, the position of dark bands are noted in relation to the Fraunhofer's lines. If a pigment shows more than two bands, they are starting from the red end, designated alpha, beta, gamma, and so on. Once again, it may be noticed that one or more positions in the spectrum there is no color and which appears as dark band. The location of each dark band, center of band, is read on the scale. If there is no scale, the position of dark bands are noted in relation to the Fraunhofer's lines. If a pigment shows more than two bands, they are starting from the red end, designated alpha, beta, gamma, and so on. Okay, thank you. चैप्टर तो पढ़ लिए बट थोड़ा सा समझने वाला टॉपिक है, प्रैक्टिकल करने के बाद ही क्लियर होगा. ठीक है, थैंक यू. चैप्टर कंप्लीट हुआ. मिलेंगे नेक्स्ट चैप्टर में, चैप्टर नंबर 10 क्लिनिकल केमिस्ट्री एनालाइजर्स. थैंक यू, बाय बाय.